Hello class. Today we are looking at how to determine the geometry of these molecular shapes, and the way we're going to decide is using VSEPR theory, stands for valence shell electron pair repulsion. And the idea is that since a covalent bond consists of pairs of shared electrons, and electrons all have negative charges, and like charges repel, that these atoms that are bonded to the central atom of our molecule are going to arrange themselves as far away from each other as possible. And knowing that, we can determine what shape they're going to be. We've got some choices here. We're only going to focus on 5 together. You can see those here: linear, bent, trigonal planar, trigonal pyramidal, and then tetrahedral. Okay. Before we get into that, let's look at kind of a visual. This is a PhET simulation that shows the repulsion of these electrons really well. Okay, and so even if I drag these are lone pairs, these are non-bonding electrons. Even if I drag them in this water molecule, try to get them close to each other, you can see they repel away from each other. And so because they arrange themselves as far away as possible from one another, then we can determine in this case that this is going to be a bent structure. If I take away these 2 lone pairs, I see that bent structure of water. Okay, and that gives it a lot of its unique properties, its polarity, and so on. If I look at some other examples, this is CO2. CO2 doesn't have any lone pairs, and so as far away from one another as these atoms can get is 180 degrees. That's as far away from one another as they can get. And then if we look at something that's got more atoms bonded to the central, this is methane, CH4, and I can see that this is a tetrahedral structure, which looks different than when we draw it in 2 dimensions on our paper. It looks kind of like a square planar structure on our paper, but in 3 dimensions, when we show it this way, we see that it's actually a tetrahedral, and that those atoms can get farther than 90 degrees at 108.5 for our tetrahedral structures. And there are bigger structures. We're not going to get into things like the octahedral sulfur hexafluoride, but it's out there in case you're interested. All right, let's learn how to decide on the shapes. And this is a little graphic that shows some of the more complex shapes, and so ones that we're not going to get into or practice with, but you can see a T shape, a trigonal bipyramidal, square planar, and so on. We're going to just focus on those 5, and so these 5 are going to be the ones that you see here: the linear, trigonal planar, tetrahedral, pyramidal, and the bent structure. And the way we're going to decide is a mix of 2 things. One, the number of atoms that are bonded to that central atom. And so, we're going to look at it. Are there just 2 things bonded to the central atom? Well, if that's the case, it can only be linear or bent. Are there only 3 things bonded to the central atom? Well, in the examples we're going to go over, that can only be pyramidal or trigonal planar. And then if there's 4 things bonded, since we're not going to deal with any expanded octets, that will have to be tetrahedral. All right, here's our decision tree for deciding on how many or what our shape is going to be. So you can see we're looking at how many atoms are bonded to the central atom, and are there any lone pairs on the central atom? And by lone pair, we mean non-bonding electrons, 2 electrons shown in the Lewis structure that aren't connecting to atoms. And so I've got some examples over here. If there's just one thing bonded to the central atom, well, really they're kind of both the central atom. There's not really a central atom there. So 2 things bonded together, it has to be linear. That's the only option. If you've got 2 things bonded to the central and no lone pairs on the central atom, they are going to arrange themselves as far away as possible, and they're just going to be this linear structure. If there are lone pairs on the central atom, as there are in water, then we're going to have a bent structure. Those electrons on the central atom are going to repel the bonding electrons down and make this bent structure. Here we've got 3 things bonded to the central atom, no lone pairs on the central atom, and so they're going to make a planar, which is just one plane in a 3-dimensional space, planar, trigonal planar, or trigonal planar. And then if we have a lone pair on the central, then we've got a trigonal pyramidal, and you can see my picture here has a wedge and a dotted line. The dotted line is meant to represent a bond or an atom that's going into the paper in 3-dimensional space, and then the wedge is coming out of the paper. So it's meant to give you kind of a 3-dimensional effect. And then tetrahedral is if there are 4 things bonded to the central atom. Okay, let's do some examples. So this is from 6.4. Should look like this, and you've got a few examples from our previous Lewis structure video to go off of. So let's use our decision tree to determine our shapes for these atoms. Here we've got CH2Cl2. This is the one we made earlier. We counted our total valence electrons, determined central atom, bonded everything to the central atom using single bonds, filled the valence shell of all of our atoms. We counted them up to make sure that they added up. And so now we need to figure out what's the shape of this. Well, how many atoms are bonded to the central atom? Looks like here's my central atom, carbon. I've got 1, 2, 3, 4 atoms are bonded to my central atom. How many lone pairs are on my central atom? I look at my central atom. I've got 8 electrons around my atom because that's why it bonded in the first place. But all of them are bonding pairs. They're all being shared between these atoms. And so there are no lone pairs on my central atom. So what's my geometry? Well, we look over here. We see that when there are 4 things bonded to the central atom, we call that a tetrahedral structure. So I'll write tetrahedral. And then since a picture kind of helps to give sort of a visual representation, we're going to draw the picture that we've got there as our example. We'll draw this picture right here because we don't want to have the misconception that this molecule looks like this. Instead, we want to show it in 3 dimensions. Okay, this is our CH2Cl2. So let's draw that. So I've got one coming off the top. In the middle is going to be my central atom, and I've got one of mine coming out of the paper this way, and then I've got one that's going kind of into the paper. And so this is trying to show kind of this sort of this tripod kind of thing. Okay, and so that's really how we're trying to represent that. It would look like kind of like this with this white one coming out at us. Okay, let's do another example. We're looking here at water. Actually, we've already seen water, but let's see why it gets that bent structure. So here's my water molecule. The central atom is oxygen. How many atoms bonded? 1, 2. Lone pairs on the central atom? Well, here's one lone pair. Here's another lone pair, so that's 2 lone pairs on the central atom. Those lone pairs are going to deflect the bonds downward. So if you think about water as bent structure, one lone pair is going to be up here, one lone pair is going to be here, and it deflects those atoms down. And so that is in keeping with our little decision chart. We've got 2 atoms bonded to the central. I do have lone pairs, and so this is a bent structure. This is bent. And draw my little diagram, my little picture there. Okay, a couple more examples. Here's carbon dioxide. I've got 2 atoms bonded to the central atom, 1, 2. I've got no lone pairs on the central atom. I do have lone pairs on these outer atoms, but not on the central atom. And so my geometry is going to be no lone pairs, 2 atoms bonded. That's going to be a linear molecule, linear. And it looks like that. All right, one final example, and then you're on your own. Okay, this time we have 3 atoms bonded to the central atom. 1, 2, 3. 3 atoms bonded to the central atom. How many lone pairs on the central? Well, looks like I've got a double bond here, single bond, nothing, no lone pairs on the central atom. You would see 2 dots if that was the case. And so 0 lone pairs. I go to my decision tree, and I see 3 things bonded to the central. If it did have a lone pair, it would be trigonal pyramidal. Okay, but since it has no lone pairs, they're going to spread out as far away from each other as possible in this trigonal planar structure. Okay, and that is 120 degrees between for each angle. Okay, our final column, polar or nonpolar, is for a separate video. We're going to be looking at symmetry in the geometry and thinking about the difference in electronegativity between the atoms to see, are the electrons going to get pulled towards one side of the molecule, or are they going to be evenly distributed throughout? But that's for another video. For now, you're ready to start identifying geometric shapes for your molecules. Have fun.